of what they can do when providing funding to get into the classroom. Now, as I mentioned, we have our educator, Sean, behind me. He has a lot of experience presenting this program, and I had no doubt you will be entertained and maybe a little bit educated with some of the science that we're going to see here. So without further ado, let's turn it over to the one, the only, Mr. Sean Carlock.
All right. Well, welcome. It's so good to have you guys here. Like Thomas said, we are having a lot of science happening outdoors right now. We've got expanding gases and plasma, all kinds of cool things. But we're going to talk about some of my favorite demonstrations that we do at the Museum of Discovery, our awesome science show. Now, I'm going to start off by showing you something that is very cool. I would go so far as to say this is probably the coolest thing you've ever seen. Maybe even the coolest thing you will ever see in your entire life. Now, that's a pretty bold statement, but I think it's true. Now, what I'm going to show you is dangerous. So I have to take a few precautions to make sure that I'm safe. I have got my glasses to protect my eyes. I have these big gloves to protect my hands. And what if I told you that this very dangerous thing that I'm about to show you is surrounding you right now at this very moment? It's in the air that we breathe. But right now, it's in its gas form. And I'm sure you guys have probably talked about solids and liquids and gases before, the different states of matter. Well, when it's a gas, it's perfectly harmless. But when you put a gas under extreme pressure and cold temperatures, you can turn that gas into a liquid. Now, in its liquid form, it's quite dangerous. And it can't exist anywhere naturally here on Earth. It's too cold. We have to keep it inside of this special container. This gas that we've turned into a liquid, nitrogen. Liquid nitrogen, negative 321 degrees Fahrenheit. By far the coolest or coldest thing you've ever seen. Now, it is a colorless liquid. It kind of looks like water. And as I pour this out, you might be able to see that it kind of looks like water, but I promise you, it is not water. Because water does not do all of this. You can see the moisture in the air around it is condensing and forming a fog. You might be able to see it kind of jumping out of the top of our beaker there, doing something a little bit unusual. Now, maybe you have seen water do this before. In order for water to do that, it's got to get very, very hot and start to boil. How is it possible that something that I just told you is extremely cold, negative 321 degrees Fahrenheit, how could it possibly be boiling? Well, it's so much colder than the room that we're in, the air and the temperature of that beaker, that's so much warmer than that liquid nitrogen, it's actually causing it to boil. That's why you see the bubbles and it's jumping around in there. Now, there are a lot of very important applications for liquid nitrogen. They use it in the medical field for cooling large magnets. They use it to burn off warts, various different things. But here at the Museum of Discovery, we just like to put things in it and see what happens. Watch. Solid, liquid, or a gas? Can't be a liquid because it holds its shape, right? Can it be a solid if it does this? Sure it can. So we would classify this as a solid, but this is a polymer. It's a chain of molecules that are held together and allowed to move and bend and stretch and line up. That's what makes a rubber band useful, is its ability to stretch and then go back to its original shape. When we put it in our liquid nitrogen, however, you can see it starts to boil from the heat of that rubber band. But after just a couple of seconds, that boiling stops because that rubber band is now extremely cold. If I try to reach in here and find one, kind of hard to see, isn't it? All this fog. Let me get some of that out of the way. Wait a minute. Look at that. You see, we have a lot of moisture in our breath. And and it's very warm. So as I'm blowing it across that liquid nitrogen, so cold, it's like when you go outside on a cold day and you can see your breath. This is what it would look like on a negative 321-degree day. Look at that. Doesn't help me see my rubber bands any. All right, there's one. Here we go. We're just going to take it out and give it a little squeeze. It just flew into pieces. Look at this. As it gets cold, those molecules do very much like you might. They huddle together and they hold themselves tight and try to stay warm. Now, when they do that, they hold on so tight that when we try to move them or bend them, they become brittle and they shatter. But after just a couple of seconds, you can see it goes right back to being stretchy again. Let's see if we can do that one more time. All right, 3, 2, 1. Look at that. You can see a little bit of fog coming off of that. That rubber band is cold enough that it's condensing the air around it. Broke it right into 2 pieces. Look at that. But after just a few seconds, it starts to warm up, starts to bend, starts to stretch, just like it did before. Pretty cool, huh? Now, I want to show you what this does to another polymer, but this one's a little bit different than our rubber band. This one, we can put something inside. See, this is a balloon. Have you guys ever seen the people who blow these up and they twist them and make animals and stuff? Raise your hand if you've seen that before. That's really cool, isn't it? Well, that's something that I used to do before I came to work here at the Museum of Discovery. I actually brought a couple of my friends along with me. Here they are, Siegfried and Roy. Look at that. Now, these guys do tricks. Check this out. Stay. He do that all day. He's just that good at it. Now, they really do some cool aquatic things in the swimming pool where they jump through hoops and swim around, but we don't have a swimming pool here for the Museum of Discovery. We do, however, have this beaker full of liquid nitrogen. Do you think we should put him in there and see what happens? Oh, do you think it's going to pop? I hope not. Let's find out. Head first. I don't know if he's going to fit in there. He's kind of big for our beaker. We'll see if we can get him inside. There we go. We should never go swimming by ourselves. Should always make sure you use the buddy system. Now, there's no way that 2 of these balloon animals should fit inside of this beaker at the same time. There must be something going on here that we're not seeing. Take a closer look. Looks like those balloons are all shriveled up inside, doesn't it? So a couple of things could have happened here. Perhaps the balloons popped and the air came out, but I did not hear any popping sounds. So this is what science is all about, is observing and making observations. I didn't hear anything pop, but I can tell that those balloons have shrunk down. So maybe we could hypothesize, perhaps somehow the air came out, even though the balloons didn't pop and they shrunk down. Maybe it snuck out of an opening we didn't know about. Well, what if the air is still inside those balloons? What could cause that air to shrink down so much that the balloons shrivel up? Remember we talked about our liquid nitrogen being a gas all around you, and when it gets cold, it condenses down and becomes a liquid? That's what happened to our air inside of those balloons. It didn't come out at all. It's still inside. It's just changed to a different state of being. It's a liquid now instead of a gas. I can prove that if we pull one out and let it warm back up. As it warms up, that liquid air starts to boil. It starts to evaporate, it starts to expand, and it takes up more space, filling up the area that it took before. Look at that. Look at that. Completely restored. Now we're going to put this one down so you guys can get a nice up close look at it. Look at this. Watch it grow. That liquid heats up because it's too warm in this room for it to stay a liquid. It turns back into a gas. It takes up more space as a gas than it does as a liquid. It fills our balloon back up, just like that. Might need a slight chiropractic adjustment, but no worse for wear. What a big round of applause for Siegfried and Roy. Yeah! Pretty cool, huh? Now, have you guys ever seen those places that have the big ball pits where you can get in there and they have all the plastic balls that you can crawl around in and jump around in? I have determined through careful observation that those balls are not good for anything else. You can crawl around in them, you can put them in big pits, but they're not heavy enough to play catch. They don't throw very well. They don't bounce very good, so they wouldn't work for basketball. One use that I have found, they're really, really good for putting in liquid nitrogen. Now, this is going to kind of take all of the things we've seen so far and put them into one. The outside of this ball is starting to get brittle, just like our rubber band. The molecules are huddling close together, holding on tight to one another. That's going to make that outer shell of that ball brittle. Now, inside of that ball, since it's hollow, there is a gas. There's air inside that is now condensing down and becoming a liquid, taking up less space than it did before and creating almost a vacuum on the inside of our ball. So when I take it out like this and go 1, 2, 3, look at that. Our brittle outside of our ball, as soon as I punctured it with my tongs, that ball imploded. That vacuum or that empty space inside from that air becoming liquid caused it to just kind of collapse on itself and kind of explode into little itty bitty pieces. I love that. Now, this is all cool, but it's kind of hard work doing these amazing things. I know, amazing scientific things. Kind of makes me hungry. So if you guys don't mind, I haven't had lunch yet. It's not quite time, but I brought these with my lunch today. Some Cheetos. Raise your hand if you like Cheetos. Me too. Me too. Now, I really like the puffy ones. I enjoy the crispy, crunchy ones, but I have never had the hot Cheetos. But I hear that they are pretty good too. Now we're going to open these up. Cheesy. I should probably say, not a good idea to have a snack while you're doing science experiments. If you weren't paying attention to what you were doing, or if you're like me and you like to talk with your hands, you might accidentally drop something into your liquid nitrogen. That wouldn't be good. That would be a waste of a perfectly good Cheeto. Because you guys saw what happened to those balloons when we put them in there, how cold this liquid nitrogen is. Well, do you think it would be a good idea for me to take those Cheetos out of that liquid nitrogen and put them in my mouth? Oh, I don't know. Well, some of you are nodding your head yes, some of you are shaking your head no. I'm not sure what to do here, Thomas. I'm getting mixed signals. Well, let's give it a try. What do you think? Now, it's very important to understand that here in a moment, I am going to put this in my mouth, but I am not putting liquid nitrogen in my mouth, okay? As soon as we take that Cheeto out of here, that liquid nitrogen evaporates almost instantly. It's too warm in this room for it to stay liquid. Woo-hoo. All that's in my mouth is a really cold Cheeto, really cold. You have to be careful you don't put it on your tongue or it'll stick, just like in the movies. Let's do that one more time. Not polite to chew with your mouth open, I know, but this is for science. You could see how it made that moisture, just like when we blow across the moisture in our breath, it changed it into a fog as it came out of my mouth. Now, you could also see how it was kind of just going all over the place, couldn't you? We're going to talk a little bit about that and how air moves by looking at a little something called a vortex. Vortex, one of my favorite things to look at. Now, if I just left our liquid nitrogen here in our beaker, it would evaporate, it would turn into nitrogen gas, and it would be all gone before we were ready to use it for our finale. So I'm going to put it right here, back inside of our dewar, where it will stay a little bit colder. Look at this. All this stuff on the side. The moisture in the room has condensed on the outside of our beaker and changed into snow. We'll make it snow in here. All right. Very good. Vortex. If I asked you what is a vortex, how many of you think you could give me that definition? Maybe a few. What if I asked a simpler question? How many of you have ever taken a bath? Hopefully, most of you are raising your hand right now. When you take a bath and you get done and you pull the plug, does that water just go straight down the drain? What does it do? It kind of goes like this, doesn't it? And it spins around as it goes. That is a vortex. Any spinning liquid or gas is a vortex. I can show you what that looks like in your bathtub using this, our handheld vortex generator. Super high-tech thing we have here. Now, you could make something like this at home. If you had a couple of soda bottles and some way to hold them together, maybe some tape wouldn't be the best option, but it would work. Now, we put some liquid inside this bottle here and left this bottle empty. If I wanted to get that liquid into this bottle, science tells me gravity will help. If I turn it over, gravity is going to pull that liquid from this bottle into that one. But watch what happens. Not a whole lot. Eventually, it would probably get there, but this is too slow. We don't have that much time. We're going to use a vortex to get this done. Spinning liquid or gas. So I'm going to give it a little spin to get it started. And there is our vortex. Isn't that neat? What does it look like? Most people say it's a tornado. Well, in the water, we would call this a whirlpool. In the air, yes, this would be a tornado. A tornado is a vortex. Look at that. Spins around. Now, right down the center of that vortex, it creates almost a tunnel or a straw-like section for the air to pass through. The air goes up the middle while the liquid runs down the outside edges. That way, the air and the liquid don't run into one another, they don't get stuck, and they trade places a lot more efficiently. So that's what it looks like in the liquid. I'm going to show you in a second what it looks like in the air. But before I do, there's another substance. I know we said any spinning liquid or gas. Well, this is a little thing called plasma. Now, you might have heard me mention it before when I was talking about the storm that's going on outside. Plasma is what you see when you see lightning, as the lightning goes through this supercharged gas in the air. It's also what you see anytime you see fire. It's another thing that we call fire is plasma. I'm going to make a plasma or a fire vortex, a tornado of fire. Need a couple of things to do that. The first is this trash can. Pretty nice, huh? Now, the reason that we have all these holes in this trash can is in order to have fire, you must have oxygen. And the fact that I am still standing and talking to you and I haven't gone boop is because there's plenty of oxygen in this room. We know it's here. The next thing that we're going to need to make fire is a fuel, something to burn. I've got a little bit of isopropyl alcohol here. I'm going to put that down inside my trash can. And last, but certainly not least, you've got to have some way to ignite your fuel, some kind of a spark or a heat source. And I'm going to use this lighter. Now, if I just click this on and touch it to my fuel, it's quite easy to make fire. If we wanted to have a fire vortex, though, we need spinning. We need that rotation. And that's why we put our trash can on this lazy Susan. Look at that. If I spin that around, look, it forms that same kind of funnel, that same tunnel right up through the center of our fire, a fire tornado. Look at that. Go the other direction, and it spins just the same. Can you imagine if you went outside and you saw something like that? That would be terrifying. Now, luckily, that's not something we generally have to worry about here in the US. Now, maybe during the wildfires out in California this year, they might have had some of these if the wind was just right. Look at that. I've been told, I've never experienced myself because I've never been to Australia, but I've been told that this actually happens from time to time in Australia, which is another reason why I'm never going to Australia. It's like big spiders and tornadoes of fire. Whew, what a place. Now, we've seen a vortex in liquid. We've seen a vortex in fire. Now we're going to look at it in the air using my super awesome cups of science and another trash can. But before we get to that, do you think if I took a big deep breath, I'd be able to blow these cups over? Now think about what you saw when you saw that air coming out while we were eating the Cheeto. Let's give this a try. Nothing. See, as we were eating that Cheeto, you could see the air kind of going every which direction. It's very turbulent. It's hard for me to focus my breath enough to push over those cups. And that's where our trash can comes in. This is a Bonafide Vortex cannon. We've changed it a little bit. Put a hole in the bottom right here and put a rubber sheet over the top right here. Now, what this does is when I hit that sheet of rubber, it forces the air inside of the trash can to come out through this hole. And as that air is moving, thanks to Bernoulli, we know that it creates an area of low pressure. That means basically that the air is going somewhere so it can't push out against the air around it. So as that air goes, the higher pressure atmosphere kind of pushes in behind it and it hits that column of air and it starts to go along with it. And the next thing you know, we get this. And now we have rotating gases. Vortex allows us to do really cool things like this. Hoo! Pretty cool, huh? The only problem is we can't see what our vortex looks like. If you move your hands to the air like this, you can feel the air around you. We can see it when it makes other things move. But we can't see the air itself. If we wanted to be able to see what our vortex looked like, we'd have to add something to our air. And that's why we have this. Now, when you see a tornado, whoop, it's picked up all kinds of dust and dirt and debris and things around it. This is going to represent our dust and our dirt and debris for our example today. This is artificial fog. We'll put a little bit of that in, and that should allow us to see our vortex. All right, are you ready? Here we go. Oh, look at that. Now, that doesn't look like a tornado, does it? But if you could take a tornado and grab it at the top and the bottom and stick those two parts together, that is exactly what you would have right there. The whole outside edge of that circle or halo, or my personal favorite, donut, the whole thing is spinning. It's all rotating. It's a circle of vortex. Isn't that neat? Do a look at this little one coming. Woo. Super slow. Just kind of hangs in the air. Now, I could do this all day long, but if I do, it'll get really, really, really foggy in here, and I'll probably set off the smoke alarms, and we don't want that to happen. So let's put that down, our vortex generator. Let's go back over here because I promised you a finale with our liquid nitrogen, did I not? Well, it is time for that finale. Now, in order to do this, we've got to have just the right amount of liquid nitrogen. And that's why it's good that our snow is gone now. We can actually read the numbers on the outside of our beaker. Let me put my gloves back on to protect my hands, because remember, this liquid nitrogen is extremely cold, negative 321 degrees Fahrenheit. We're going to pour some inside our beaker. This is kind of hard to tell exactly how much you have, because remember how it jumps around and it starts to boil. A little bit more. Perfect. Yeah, maybe a little bit more. All right. There's our liquid nitrogen. And we're going to add to it some boiling hot water, 212 degrees Fahrenheit. That's a difference of over 500 degrees. And if we did that inside of this glass beaker, it would shatter into a bunch of pieces, and Mr. Thomas would not appreciate that. So I'm going to get something to put our liquid nitrogen in that'll be a little bit safer for this particular demonstration. A metal container with this metal pitcher inside. We're going to put the liquid nitrogen down inside of that pitcher. Just like that. And then our boiling hot water. Now you can see the steam maybe coming off of this a little bit. Looks kind of like our liquid nitrogen, the way that fog comes off of the liquid nitrogen. But the difference is this is really hot and our liquid nitrogen is really cold. So this would be steam, and that is a fog that's being created by the moisture in the air condensing because it's so cold. Evaporation, condension. Condension, is that even a word? Condensation, that'll work. Here we go. Our grand finale. 5, 4, 3, 2, 1. Oh, wow. Look at that. That was awesome. As soon as we throw that water into our liquid nitrogen, it causes all of that nitrogen to want to evaporate instantly and become a gas. And remember how we talked about gas takes up more space than what liquid does? So you have this rapid expansion of all that liquid as it becomes a gas. There's not enough room for it inside of our pitcher. So because of the shape of the pitcher, it wants to shoot out the top. And that was that big cloud that you saw coming out. So now all we have left inside of here is just some really cold water. You can see how the fog from it is coming out and kind of dropping down instead of going up like our steam does, because this is cold air now. Look at that. That was so cool. Well, I hope that you all enjoyed our awesome science presentation. I'm so glad that we weathered the storm together. We're able to stay connected. We do have some time now that we'll be able to answer some questions. So Mr. Thomas is going to have you guys, if you have a question, go ahead and raise your hand and he will call on you and see who has a question about what we just saw here, or maybe some of the science behind our awesome science demonstrations.
All right, let's give a round of applause for Sean. What an awesome show. I really enjoyed that. I hope you like the camera angles I was able to get. I was trying my best. Let's see. Let's pull over some of our. Here we go. And Mr. Campbell, if you will do us a favor and call on the students, then they can unmute themselves and ask their questions. So if you want to go ahead and call on the students, we will get the Q&A rolling.
How did it feel when you ate the Cheeto?
All right, I think you're going to have to ask that one again, please.
How did it feel when he ate the Cheeto?
Mr. Carlock, how did it feel when you ate the Cheeto?
Very satisfying and cheesy. But I think the answer that you're looking for is extremely cold. We're not really sure just how cold that Cheeto is when we put it in our mouths, but it's really, really cold. If you've ever tried to bite ice cream, it would be like that, but even colder. So if you have sensitive teeth at all, it can be a little bit uncomfortable. You have to be careful that you don't get it on your tongue, because that's extremely cold and it'll actually kind of burn the skin and the taste buds on your tongue if you're not careful.
Yeah, I know it sounds weird, but we've actually been through training on how to eat a frozen Cheeto. So we take safety very seriously here. And so we want to show y'all really spectacular stuff, and we have to figure out how to do that in a safe way. Very good first question. Mr. Campbell, who do we have for our second question?
How come when a fog was on a desk, it didn't make the desk wet?
Ooh, super good question.
Well, it's wet now.
Yeah.
So how come when the fog comes off on the desk, it doesn't make the desk wet?
You know, I'm going to jump in there and I'm going to say that it actually did make the desk wet a little bit. So it's going to cause some dampness on it, but it's not going to cause like big droplets. So we have seen, like I've done this in the past, where if we're doing this type of a demonstration, the fog will roll onto the desk and then you'll see the very thin layer of water. So if you were to wipe it with a rag, you would actually see that it would be damp. So even though you couldn't really see it, it did make it just a little bit wet. That's a really good observation.
Yeah,
I like
now
that.
I'm gonna have to feel it now next time and see just how wet that is, because that moisture has to have something to grab onto. So it would have to have something there on the top of this in order to form droplets, and we probably would need more fog before it would really accumulate into something that you saw really well. But I'm gonna have to do some science on that. Very good question.
What's our next question for the morning?
Inside of the white bucket thing, is it just fog inside of it?
Are you talking about inside of here?
Yes.
So inside of here is all of our liquid nitrogen. So it's kind of would be like if it was full of water, except really, really, really cold water. There is, however, going to be nitrogen gas that's coming out as it is warming up and it's evaporating and turning back into a gas. That's the reason that this lid is loose. If this lid was super, super tight and sealed on there so that gas couldn't come out, it would build up pressure inside as that liquid changed into a gas. That pressure would build up to the point that this would go boom. And we don't want that to happen. So you always have to have a way for that gas that is forming as that liquid evaporates